Hello, everybody. We're going to be giving you a presentation and general overview of black holes and the phenomenons associated. There are three kinds of black holes, or three primary kinds. There's stellar mass, supermassive, and primordial.
So stellar massive black holes, the formation are formed when stars go supernova and collapse. And in order to have a stellar mass black hole, you need to have a mass 3 to 100 times the sun's current mass. They can be found in binary star systems where they interact with a companion star, pulling matter together to form and emit X rays. Over time, they can grow by accreting matter from nearby stars or merging with other black holes.
All right, so supermassive black holes. And this slide is going to include the latest research because it's still uncertain how supermassive black holes form. So the first thought is that it's caused by when two stellar mass black holes collide, and this happens many times over. There's many black holes that merge to eventually form a supermassive black hole. So that's one theory. And then another theory is the collapse of massive gas clouds, and this suggests that instead of forming from the death of a star or things like that, that they form directly from the collapse of enormous gas clouds in the super early universe when it was still dense enough for that to happen. And then the third theory, and this I think is the most recent and probably the most experimental theory, or out there theory, is the primordial star theory, which was that in the very early universe, there were stars that were much more massive than modern stars. And they were so massive that their cores actually collapsed into a black hole, but the stars were able to maintain fusion because they were just so huge. And the pressures were so enormous, and then eventually these enormous stars finally collapsed into the black hole after losing enough mass, and that's where these supermassive black holes came from.
So primordial black holes, they're a set of hypothetical black holes, as Andre pointed out, that formed less than a second after the Big Bang formed by gravitation collapse due to the density of the universe. Because right after the Big Bang, the universe was so hot and compact, it had immense amounts of density. They can be used to explain very large redshifts of early galaxies found by the James Webb Telescope. They can also be used to explain the dark matter problems and string theories that we currently have in science that are not yet proven.
All right, so let's get on to the types of black holes. So there are three primary types of black holes. There's Schwarzschild, Kerr, and charged.
Okay, so the properties of black holes is very simple. There are only three properties of black holes: the mass of a black hole, the spin of the black hole, and the charge of the black hole. And it's kind of cool because they're very similar to elementary particles in this aspect, like electron. Also, the only difference between electrons are the mass, the spin, and the charge. Um, so that's how you can define and describe black holes. Schwarzschild black holes, first discovered in 1916 by Carl Schwarzschild, soon after Einstein's general relativity theorem. It was a equation, like a solution to Einstein's general relativity theorem, and it was theoretical. And black holes weren't actually observed until much later. Schwarzschild black holes are the simplest type of black holes with no spin and no charge, but this also means that they don't really exist in our universe. Because black holes are created from the collapse of spinning supermassive stars, we all know that angular momentum must be conserved. So when the star supernovas and condenses and collapses into a black hole, that momentum is still conserved. Therefore, the black hole will continue to spin and spin even faster than the star did because it's so much smaller.
Okay, so Kerr black holes. These are the most common form of black holes in the universe, and like Will said, they derive their angular momentum from the spinning star that they were formed from. And depending upon how fast they're rotating, they can have some super crazy effects and disturbances on space time surrounding it. And basically, the primary aspect of these is they have a feature known as frame dragging, which is essentially a region where the black hole's angular momentum is so strong and its gravity is so strong that no object can stay still within that region. It has to spin at the same rate as the black hole spins. And this region is called the ergosphere. And it also can have some strange effects on time. It's theorized that if you were to enter the ergosphere, you may be able to travel into the future because general relativity, you'd be moving so rapidly around the black hole that you would be transitioned to the future. And then it's also possible to extract energy from a Kerr black hole. We'll get to that later. And then the final thing is, and this is really weird, Care black holes are theorized to have a ring-like singularity, which is strange because a singularity is already a one-dimensional point of infinite density. So you have to make it into a one-dimensional ring of infinite density. It's very strange. We're not really sure what's going on down there. It's all hypothetical. And then the final type is charged black holes. Now, it's unlikely that either of these two types of black holes actually exist. They're only theorized. If they did exist, it was probably in the early universe. And the reason for this is because as black holes absorb matter, they'll naturally reach a neutral charge state. So only super young black holes that were formed maybe a couple of seconds after the formation of the universe itself could have been very briefly charged. And so these black holes are entirely theoretical and probably don't exist at all.
Okay, so that leads us into the structure of black holes. So, in general, these are the structures of the black hole. You have relativistic jets, you have the event horizon, you have the singularity, you have the photon sphere, you have the accretion disk. It's not on this map, but if it's a Kerr or a spinning black hole, you'd have the ergosphere. And we're going to go into each one of these structures in detail.
Okay, so the event horizon. I'm sure you probably all have a general idea of what the event horizon is, but it's the point surrounding or the diameter surrounding a black hole from which the gravity is so strong that nothing can escape no matter how fast or how energetic. Not even light can escape. Um, and this is kind of interesting. If you were to pass the event horizon to an external observer, they would see you stop at the event horizon and slowly get redder from the redshift and then completely disappear as your light faded into the infrared spectrum. However, from your perspective, you would keep falling into the black hole. And depending upon the size of it, you may actually live for a significant amount of time. If it's a small black hole, the gravitational differential across your body would spaghettify you. And that's something else we'll talk about later. But if it's huge, there won't be a massive gravitational difference across your body. So you could continue to fall into the black hole for a very long time, presumably. Yeah, so that's the event horizon. And then you have Schwarzschild event horizons, same deal, non-spinning, pretty self-explanatory. And then Keir event horizons, also very similar. There's a possibility that in the ergosphere, since these are spinning, that beyond the regular event horizon, there's a point where predictability and time essentially stops existing, and we don't really know what goes on in there. It's entirely theoretical if that place even exists, but the idea is that there would be no like space the fabric of space-time, if you want to call it that, wouldn't even exist in that place. So it's almost like a non-existent place within the black hole.
Okay, and then you have the singularity itself. There are two types of singularities: the ring and point singularity. So first, you have singularities are at the quote unquote center of black holes, but since like on the inside of a black hole, it gets all wonky, and honestly, it space time actually flips once you pass the event horizon. So space is infinite, but time is finite. Unlike outside of a black hole, where space is finite and time is infinite. So you actually, it's not like a, it's not the center of the black hole is actually just the future. So your future is the singularity. Um, and as we said, space-time curvature at the singularity becomes infinite. And for points, it has no volume, infinite density, and the entire mass of the black hole. So point singularities can only occur with the Schwarzschild black holes, and it's a zero-dimensional point. Um, and you will fall into the singularity because it's in your future once you cross the event horizon. Of course, as we said earlier, you would be crushed to infinite density and mass, and you will be added to the total mass of the black hole. And then you have ring singularities, also known as ringularities. These occur in Kerr black holes. It's a zero-dimensional ring due to the spin of the black hole. It is possible to like miss the singularity. And it's also theoretically possible to fall through a wormhole and time travel, but yet again, it's all theoretical because currently, with our understanding of physics, this could not be possible. But if you push the ideas of ringularities to the extremes, it may be a possibility. The issue is it starts leading to time paradoxes, like the grandfather paradox, where you go to your own past. And along with that, ringularities since they're disc shaped, this is what actually causes the ergosphere around curved black holes because it spins. Therefore, the area around, like the entire space time around the angularity, spins with it. Um, and also, singularities are entirely theoretical in general, and they have all singularities in every black hole are identical because, as we said earlier, there's only three properties of black mass, spin, and charge. So if you could somehow take all the singularities from every black hole, they would all be entirely the same. Just as like if you could take every single electron, they would all be the same.
All right. So the accretion disk surrounding a black hole is essentially the matter that the black hole is consuming. And the reason it glows like it does is because this matter is spinning around the black hole at an incredibly high speed, and it's essentially colliding into itself. The friction between the matter in the accretion disk is so high that it reaches temperatures exceeding 10 million Kelvin, causing it to emit a lot of X rays and gamma rays, and even some visible, depending upon the accretion disk, where in the accretion disk you're looking at. And this is also in a plasma state, so it's been ionized. The atoms are stripped of their electrons. And then there's different areas of the accretion disk. Obviously, the innermost areas are the hottest. And then as you progress outwards, it emits longer and longer wavelengths, eventually getting to IR, where you can no longer see it with the visible eye, and we can only use our telescopic instruments.
Okay, and then along with accretion disks, you have relativistic jets. These are beams of ionized matter that travel close to the speed of light, and they can extend up to millions of parsecs. And this causes relativistic beaming due to like its speed near the speed of light. So, say if the jet is moving towards like you or an observer, it'd be like a lot more luminous and a lot more bright. But if the jet is moving away from the observer, it'd be a lot more faint and dull. And there's two current candidate theories for like how these relativistic jets work. First, you have the Blandford-Zanac process, which is where the jets extract like the energy from the magnetic field around the accretion disk, and then it drags and twists that matter by the spin of the black hole, uh, which launches the relativistic material up into space due to the like strong magnetic field lines. The other theory is the Penrose mechanism, which uses frame dragging, which is where the space along the accretion disk is dragging as well to extend relativistic particle energy and momentum. So basically, like shoots out. And then next, you have the photon sphere. So this is an area around a Kerr black hole where light essentially orbits perfectly. Um, and this is very, you get some interesting concepts here to where if you could, obviously it'd be like millions of degrees, but if you could like stand in the photon sphere, since the light would be circling around, you could see the back of your head.
All right. So the ergosphere. This is something I talked about earlier, but I'm going to go into more detail on this slide. So, like I said, this is an area where any object is forced to move with the same rotational velocity as the black hole. And since the black hole's gravity is so strong, it also drags space-time along with it. So it's essentially as though the floor you were standing on was being moved. So you have no choice but to move within the ergosphere. And then, of course, in a non-rotating black hole, there is no ergosphere. And then, yes, frame dragging, Kerr black holes don't have this. And then there's this thing called the static limit, which is essentially the outer boundary of the ergosphere, where any object that moves at the speed of light is just it stays still to relative to an external observer because it is moving at exactly the same rate against the ergosphere's rotation. And then, as I mentioned earlier, you can extract energy using the Penrose process.
Okay, so as we briefly touched on earlier, there's this process of spaghettification, and this can only happen with like small black holes. So think of like stellar black holes, and it's due to the small radii of these black holes that the gravity would be so intense when entering it that if you were like standing up straight while entering, your feet are closer to the black hole and the gravity is so much stronger on your feet than your head that it like pull you into like essentially a piece of spaghetti and like tear your limbs. So this would not be a great process. But as said earlier, it's only a risk with smaller black holes because in much more like supermassive black holes, the radii is big enough that the gravity would not do this to you.
Okay, so gravitational lensing, and this sort of relates to the photon sphere that Will mentioned. But since the gravity of a black hole is so immense, it can bend light around it, which means that since we of course can't see black holes since they absorb all the light that comes near them, but we can see the gravitational effects that they have on the light surrounding them if they have, say, a galaxy behind them. And so there's a couple of types of gravitational lensing that can occur with a black hole. The first is an Einstein ring, which is just a circular ring of light formed around the black hole when it's directly between the light source and the observer, which would be our telescopes. And there's multiple images where it can essentially duplicate the image behind it. And this is where the thing behind it that's emitting the light is set off at an angle. So the black hole can bend the light around itself multiple times. And then eventually we see it as multiple images. And there's magnification. This happens with the most distant and the brightest of stars. And then, like Will already talked about, the photon sphere, where they can essentially orbit the black hole.
Okay, and then there's this concept of gravitational time dilation that we briefly touched on earlier. So, from a distant observer, clocks would appear to tick slower, like close to a black hole, than say like on Earth, and that effect is known as gravitational time dilation. If you've watched the movie Interstellar, the water planet is a good example of this due to its proximity to like a black hole. So every 1.25 seconds spent on that planet equates to 1 hour and 38 minutes on Earth. And the closer to the event horizon, the stronger the gravity, obviously. Therefore, more time would even stretch. So if you were falling into the event horizon from an observer, it would appear to take an infinite amount of time to cross the event horizon. And while that's happening, you slowly fade to red light as your electromagnetic waves get pulled and stretched. Meanwhile, if you from the observer of the person falling into the black hole, you would not notice these effects. Time would appear constant, and you would just fall into the black hole. Uh, and as you're falling into the black hole, it would appear to like envelop you as the universe becomes smaller and smaller until it just becomes a tiny speck of light. And as this is happening, you would see, say, if you could see galaxies, it would appear to move really fast.
Okay, so the way that black holes die is theorized to be Hawking radiation. And as the name would suggest, this was theorized by Stephen Hawking in 1974, and it's based on quantum mechanics and general relativity. And essentially, what it suggests is that black holes aren't entirely absorbent and that they can emit radiation and they lose mass in the emission of this radiation. And this is the process by which a black hole would eventually evaporate and die. So how does this work? So in a vacuum, quantum fluctuations can cause the creation of particle-antiparticle pairs due to quantum uncertainty. And the way that this can affect black holes is what happens normally is these pairs annihilate each other instantly. But if they form near a black hole, one particle can fall in and then the other can escape, making it appear as if the black hole is radiating particles. And the way that energy is lost through this process is that since that one particle escapes, you've essentially added a particle to the universe, and this violates the conservation of mass. So, in exchange, that particle has to take some energy from the black hole to annihilate itself and preserve conservation of mass. And the slow taking of energy from the black hole by these particle antiparticle pairs eventually causes the black hole to lose all of its mass and evaporate. And this process actually speeds up as the black hole gets smaller, and this is because the gravity at the event horizon, as the black hole becomes smaller, gets more concentrated. And the greater the gravitational force, the higher the frequency of these quantum fluctuations, which causes the creation of more particle antiparticle pairs, and thus more Hawking radiation as more of these particles escape and take from the black hole in order to annihilate themselves and preserve the laws of physics.
Okay, so you might be asking, how do we observe black holes? They've been a mathematical and theoretical concept for a long time. But in 1995, astronomers started tracking stars' motion around Sagittarius A, the nearest supermassive black hole. Um, and as you can see in the bottom right corner, the Sagittarius A actually like warps the orbit of the stars around it. And due to its small apparent size and large mass, the only thing it can reasonably be that we know of is a supermassive black hole. Another way we've observed black holes is with the Laser Interferometer Gravitational Wave Observatory, aka LIGO. And in 2015, they made the first ever observations of gravitational waves of black holes. And when black holes collide with each other, they have these gravitational ripples that can be sensed through very sensitive technology. And that's what LIGO picked up. And then lastly, this might be the most infamous picture. The Event Horizon Telescope in 2017 first captured a picture of Messier 87, where you can clearly see the accretion disk around the black hole.
Okay. So now we're going to move on to scientific mysteries and the possible explanations to these mysteries associated with black holes. So the first mystery is information paradox. So one of the fundamental laws of the universe is that information cannot be destroyed. And the problem that black holes present is that anything that enters a black hole appears to be permanently lost and cannot be recovered. And then, even if the black hole evaporates via Hawking radiation, as far as we can tell, there is no way to gather data from emissions of Hawking radiation. So, this presents a huge problem. So, there's a lot of solutions to this. And Stephen Hawking's original view was that black holes somehow actually do permanently erase information, which means we'd have to re-examine quantum mechanics and basically re-examine all of our like a lot of physics. So other theories were of course made because that's kind of a wild thing to think. So information escapes in Hawking radiation. This is a I think a theory that Hawking came up with afterwards, and that there is some way that we just don't understand to derive information from Hawking radiation, and we just don't understand how. There's also a holographic principle, which is that this relates to the event horizon, how an outside observer would see you slowly fade away. It's possible that nothing ever actually fully fades away, and there would still be very subtle or electromagnetic waves that could be detected, and they would essentially act like a 2D hologram on the quote unquote surface of the black hole, which would be essentially its event horizon. And then there's this whole wormholes and firewalls theory, and this is that wormholes might allow information to escape, and then the firewall thing, there's a whole slide for that. And finally, that in black hole remnants at the moment of evaporation, they leave behind some sort of emission or something that we could have information in. So here's holographic principle. Um, like I said, it just suggests that information is somehow stored in a 2D hologram on the surface of the black hole, but it could encode 3D information, which would mean that the black hole doesn't destroy information, then that we could recover it. This was proposed by Leonard Sussex and Gerhard Hooft in the 1990s, and it was developed based on string theory and quantum gravity. And then it was inspired by the ADS CFT correspondence. And essentially, it's the idea that higher dimensional space can be described by a lower dimensional boundary. And then obviously, I explain how this solves information paradox. And then the implications is this theory could unite general relativity, quantum mechanics, and thermodynamics because it would be in accordance with the laws of each of those theories. It also supports the idea that space-time itself may emerge from quantum information, so that like the whole quantum system could be the underlying works from which relativity emerges. And then it could also suggest that black holes aren't information sinks, but they actually are just massive hard drives or data storage of the universe. And then the Hawking radiation carries information theory, is that the absolutely minute fluctuations near the black hole could be detected with the most sensitive instruments and could have information derived from them. And then here's sort of the ways they could escape. They might escape via quantum entanglement, where pairs of particles form near the black or the event horizon remain entangled. And this entanglement could mean that we could get information from inside the black hole with an outside the black hole entangled particle. And there's soft hair theory, and this one's kind of it has a funny name, but it's essentially saying that there's like a quantum hair on the event horizon of the black hole, similar to hologram theory, not quite the same, that could carry information. And there's page curve and unitary, which predicts that the black hole radiates information that leaks out in a predictable and constant way. And then this theory supports quantum mechanics. It does not. It is not in accordance with relativity, and challenges the traditional view that black holes are information erasers and suggests that black holes act like a more complex quantum system rather than just a matter sink. And then firewall hypothesis proposes that the black hole's event horizon is not smooth, but contains a sort of high energy barrier that destroys anything falling in. And this does contradict both general relativity, so maybe not the greatest, but it prevents information loss by burning up infalling matter instead of letting it actually cross the event horizon. So essentially, the infalling matter is released as energy, and the black hole exchanges that for mass. And it suggests that Hawking radiation is entangled only with the outgoing radiation from the burning of the material that's going into the black hole. And unfortunately, this also breaks traditional quantum mechanics. So we're kind of two big no-nos here. So this theory is unlikely to be true. As I say here, it violates general relativity. So it also violates quantum mechanics. And it has a big lack of observed signs or any real evidence. But it's not one of the theories. And then the final theory is the quantum gravity approach. And this aims to unify both quantum mechanics and general relativity to provide a deeper understanding of the fate of information that enters black holes. And so there's sort of two approaches here. There's the loop quantum gravity theory, which proposes that space-time is made of discrete loops rather than a continuous fabric, and predicts that black holes may not have true singularities, but instead lead to a quantum bounce which could preserve information. And then there's the ER equals EPR conjecture, where quantum entanglement, or EPR pairs, are fundamentally linked to wormholes, or they're called Einstein-Rosen bridges if you're in the know, I guess. And it implies that black holes may be correlated to the outside universe through quantum black holes, like we talked about with the ringularities, that could allow information to escape through them. And then here's some other black hole related topics. So Penrose spheres and using black holes as a generator. So this is an idea that would harness the power of Kerr black holes and their rotation. So it would be possible to go into the ergosphere, take a ton of rotational momentum from it, and then release a small part of mass into the black hole, allowing you to escape from the black hole's ergosphere and carry with you a ton of energy. And you could theoretically, up to 29% of the black hole's rotational energy could be extracted for, which is way, 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 way unbelievably more efficient than nuclear fusion, which only converts 0.7% of mass into energy. This could convert 29%. And the other benefit is that since black holes have such an unbelievably long lifetime and are so massive, it's essentially gives us access to an almost infinite amount of rotational energy, which can be converted into whatever sort of power you'd like. Um, and then this is a further on this. You could also extract energy from the magnetic field of a black hole. Basically, we would use those powerful energy jets, and you could build a much more advanced civilization. Could build a system to harness the magnetic power of those energy jets from a quasar. And this is goes into a whole other thing of Kardashev scales, but that's just power needs. A more advanced civilization than us could build these. They're physically possible. They don't violate any currently known laws of physics, and they would be exceptionally useful to a civilization, say at the end of the universe when energy has become exceptionally difficult to come by. These black holes would be some of the final things to exist in the universe, and thus could provide a safe haven for civilizations that last into that time.
Okay, adding on to that, there's this concept of a black hole bomb. So, similarly, another way to harness the energy through a Kerr black hole is to have a mirror fully enclose the black hole, similar to the idea of a Dyson sphere, and it needs to be outside of the ergosphere. Um, and then you have a hole or a window to shoot electromagnetic waves at the black hole, and then the waves will hit the black hole at the speed of light, and a small proportion of the waves will fall into the event horizon, but then a larger portion will travel through the ergosphere. If you remember, like the photon sphere, a large will just keep cycling, uh, and the black hole's rotational energy will amplify the waves. And this begins a concept of super radiant scattering, which is just a fancy term for the light to rotate and then bounce out into a mirror, which then bounces it back into the ergosphere and then it loses a small portion, but it still has a large portion that rotates and it amplifies more and then bounces out and bounces back in. And there's different things you can do with this. So if you were to open up more windows and mirrors to collect the waves afterwards, you would essentially just gain energy. It'd be another way to harness energy of a black hole through advanced civilization, because at the same rate of you putting energy in, you get even more energy coming back out. But if you were to not open up the windows and let the light escape, this could create a black hole bomb, which essentially would mean that the heat and energy from all the waves would supernova, similar to like a star, because the pressure is so much, and a supernova is essentially the biggest explosion you can create in the universe. So this would be a possible way to create a supernova. Black hole stars. So black hole stars are theoretical and they may have never existed, but if they did, it would only be possible roughly between the first zero point 0.1 and zero point 0.5 billion years of the universe. And they would have burned brighter than galaxies, and they were like massive. They were 800,000 times the solar radius of the sun. And these could only form in such the short amount of time due to the high density of the universe back then. The density would create these structures of dark matter called dark matter halos, and where it essentially like amplifies the gravity even more. So we've gone over star formations and how like gases will pull together, hydrogen will pull together, and then it will create a star. But then, uh, due to the solar ejection, it will push the rest of the gases away. Well, the mass of these stars were so insane. They had hydrogen clouds of 100 million solar masses, and these would pull together to create extremely like unquantifiably big massive stars. So much so that even after the birth of these stellar stars, the winds were not stronger than the gravity, so more gas would be pushed in, just making the star bigger and bigger. So the star would be up to 10 million solar masses, which at that pressure, the core would actually collapse into a tiny black hole. Um, and usually, when a star collapses into a black hole, that's it's like death. But since this star was so big and so massive, it would actually survive this process. So now there's a black hole only 50 to 500 kilometers inside this super massive star that's on the size of like a solar system. And typically, accretion disks, when it heats up, it slows down the process of which black holes can gain mass. But due to the gravity and pressure from the star pushing in on itself, it actually essentially like feeds the black hole. Um, so over like the next few million years, the black hole will continue to grow and become like thousands of solar masses. And then, due to the size and mass of the black hole, the accretion disk becomes even hotter than what it previously was, which then heats up the sun, which then causes the star to expand even more, up to over 30 solar systems wide. And then at this point, it's on its like last breath. The magnetic field would be so intense in the sun's core that it'd create unbelievably massive relativistic jets, and it would explode, leaving a black hole with about 100,000 solar masses. And while this is all theoretical, it would be one solution of how each like galaxy has its own supermassive black hole in the center. Because currently it's impossible given the way we know how black holes transform and grow. We are like a couple like 100 billion years ahead in the size and mass of black holes than where we should be given our current knowledge. But a black hole star could explain this massive black hole in every galaxy. So another theory is the black hole creator theory. um, so the radius of a black hole is directly proportional to its mass. This is using Schwarzschild black holes, which are the ones that don't spin. There's equations for the black holes that do spin for Kerrs, but for the sake of this presentation, it's not worth getting into that math. So for the radius of a Schwarzschild black hole, it's 2 times the gravitational Newton's constant times the mass over the speed of light squared. And the density of a black hole is infinite due to its singularity, but there's this thing called effective density, which is essentially trying to represent of what the average density would be like in a black hole. And the equation for effective density of a black hole is the mass divided by the volume. And since a Schwarzschild black hole doesn't spin, it's not obsolete, it's a sphere. The volume of a sphere is 4 pi r cubed over 3. So if you plug in the radius into this density equation, you get this equation at the bottom. And noticeably, you have the 1 over mass squared, which is important because it shows how the effective density of a black hole decreases with mass. Now, this is like really interesting because if you were to have ton 618, the largest known black hole that we have uh, like seen, it would be roughly the same effective density as air. Um, a Yeah, and a black hole with like all of the mass of the observable universe would create a massive, supermassive black hole 10 times larger than the observable universe. And because of this like idea, um, it could be possible. It's a off the wall theory, but it could be possible that we are actually inside of a black hole. And you might be saying like, well, we know the universe is expanding, and how would we be able to observe that if we were from the inside of a black hole? But if you remember, inside of a black hole, we think space and time swap, so space is infinite and time is finite. Um, so at the end of the universe's lifetime, inside the black hole, it would like rebound. It would it would condense into a singularity and then rebound again into an entirely new universe. But from outside, it would appear just as a black hole. Um, so essentially, you could look at it and you could look at a black hole and you wouldn't ever know, but there is a theoretical possibility that there's universes inside of the black holes. Um, the issue is due to like the Big Bang's chaoticness and unpredictableness, each universe may have ever so slight changes in like fundamental values such as gravity or other fundamental constants such as that, which leads to this like really interesting, almost like uh, life's different evolutionary genes of universes, to where some universes may be more able to predict to create stars and planets and black holes, while some may not. So you have this interesting evolutionary like survival of the fittest for universes as a instead of like organic organisms, because you can have universes the universes that have the highest capabilities to create black holes would then therefore be the most common ones. And this is just kind of cool to think about because that would mean our universe is probably one of those universes. Is if of course this would all was all true, which we would never know. But it's just cool to think that these universes that are created to create black holes would also probably then be able to create life in each universe. So yeah, and then last, there's naked singularities. This is also a really debatable concept among astrophysics physicists and astronomers currently. So the idea is that you have black holes, curved black holes, or charged black holes, which may not even exist. But if you were able to overpower the force of gravity in those black holes, the event horizon would like collapse and it would just leave the singularity. Obviously, we're not even sure if this is possible. A lot of people don't think it is, because say if you take a charged black hole, the more you charge it, the greater and greater like the repulsion force is going to be. So say if you were to shoot like electrons into a black hole, which have a proportionally small mass, so that way the black hole doesn't grow much but has a large charge. Um, Probably eventually the electrostatic repulsion will overpower the the sh- the the gravity, and the black hole won't observe electrons anymore. And then this similar concept also applies to spin. But say there have been theories that say it is possible to overfeed a black hole if you shoot a just large enough object with just enough spin right before its limit for spin. It may possibly break down the event horizon. And if it could, this would leave a naked singularity, which in and of itself breaks physics entirely. Um, because a singularity is a point where space time, like the space fabric, just doesn't exist with infinite density and infinite energy. You couldn't no longer predict things and say like it could just create a galaxy or create anything from seemingly nothing, which just breaks all laws of the universe. And this is why a lot of people just don't think it's possible, and why it appears that like black holes do have event horizons, because there may be some greater force in the universe or some unknown law that keeps naked singularities within black holes, so we can't observe them. So therefore, our physics don't break down.
Okay, so this is one final and very off the wall theory for what black holes could actually be. And this is the gravistar theory. And basically what this proposes is that when stars die, of course, they usually become neutron stars or black holes. But maybe there's a third possibility. Maybe the core collapse is so extreme that it causes the atoms surrounding it to be crushed into a new form of almost purely energy matter. So basically, energy made into mass. And then this forms an expanding energy bubble that would be held in check by an ultra thin, unbelievably strong exotic form of matter that forms because it's compressed so powerfully at the moment of collapse. And this would create a small object comparable to the size of London with the mass of at least 10 suns. It would also be the coldest object in the known universe. As I said here, about a billionth of a degree above absolute zero. And the structure of it would have a shell about 4 atoms thick, but it would probably be the strongest known matter in the universe. In fact, it would take the energy equivalent of a supernova to stretch the shell across the whole diameter by 1 meter. And then inside the shell is a perfect vacuum that's filled with ultra condensed energy. And then observing a gravistar would be very similar to a black hole because it would have huge mass, and because of its huge mass, there's a crazy gravity, so it trap light. It could form an accretion disk, and it could warp time. However, this proposes there is actually no event horizon, and that the real event horizon is the shell of the gravistar. And then the challenge with detecting this is that black hole collisions create sharp gravitational wave signals, while gravistar collisions should produce long echoing waves, kind of like a gong. So it'd actually be easier to detect the collision of a gravistar than a normal black hole collision. And the reason this theory may work is because it fixes all the problems with information being lost to black holes. Because the information isn't lost, it just hits the shell and becomes part of it. It makes the shell larger, but it doesn't actually go anywhere. Um, of course, this brings up another problem, which is the exotic matter shell out of which a gravistar would be made. We don't even know if that form of matter exists or if it's possible. And the idea of a super dense vacuum. The way this idea works is that space time is actually a medium. Similar, it's like the water on which the everything floats, and that you could condense this space time medium into something like a super dense sort of energy, but it would still be a vacuum. So that's another question that arises from these that we have no idea if it's possible or not. But this could be a game changing theory that would fix just about all the problems that come with traditional black holes. Of course, bringing up some other ones, but it could fix the fundamental paradoxes that black holes create. All right. So that concludes our long presentation. We hope you enjoy. We hope you learned a thing or two. And thank you for listening.
Bye.